In this section, we're going to go over some more probabilities, but in this case, we're going to talk about area. So here, let's think about, let's recall what a relative frequency histogram is. So here, we have a relative frequency histogram for the emission of a sample of only 65 vehicles. So notice that what happens if I increase my sample size. Instead of 65 vehicles, let's say I get a sample of 200. Then it's kind of likely to see that the number of rectangles will probably increase. So these rectangles will probably get skinnier and skinnier. So here in words, if the sample were larger, we could make the rectangles, I guess, skinnier or narrower, right? So if I increase the number of samples, it will probably look like this, right? So these rectangle will get skinnier. But what if I keep increasing my sample size? Then my rectangles will probably get skinnier, or I guess the number of classes will probably increase. But what if I keep doing it over and over, keep increasing my sample until I get the whole population? Then you kind of see like the curve here will get smoother and smoother. So we're probably going to have like an image like this. Like this, where the area underneath this curve now is the proportion of emissions from our population of vehicles. So this is what is called a probability density curve. So this is a probability density curve. And this is what the theme of this section is. So let's go over some definition. The curve used to describe the distribution of a continuous random variable is called the probability density curve of these random variables. So a couple things you want to note is that the probability density curve tells us what proportion of the population falls within any given interval. So there's a couple ways to interpret this. In general, the area under a probability density curve between any two values, A and B, has two interpretations. First one being that it represents proportion of the population whose values are between A and B. So for example, here, if I knew the area between 3 and 4, so here, then I could say that the proportion of our vehicles, all the population of the vehicles that spits out specific like emissions between 3 and 4 is the area underneath here. It also represents probability that a randomly selected values from the population will be given between A and B. So if I want to know the probability, the probability of getting a vehicle whose emissions falls between 3 and 4, then it will be the area underneath this curve here, if I knew the area here. So those are two ways to interpret area, probability density curve. Also, one important fact that you want to know is that the area under the entire curve is equal to 1. And if you recall that when we did the relative frequency, if we take the sum of it, it should be equal to 1. So that's the same idea here. If I took the area of everything underneath the curve, it should be equal to 1. Let's do a couple examples. So the following is a probability density curve for a population. So let's consider this probability density curve. And we know that the area between 4 and 6 is 0.16. We want to know what proportion of the population is between 4 and 6, since since area underneath curve can represent proportion, we could say that this is just 0.16. But what if you're asked that if a value is chosen at random from this population, what is the probability that it will be between 4 and 6? So this is asking for probability. So another way to use notation, this is asking what is the probability this random value x, I'm just going to call it, is between 4 and 6. Well, since we know the area underneath the interval 4 and 6, which is 0.16, this is going to be equal to 0.16. Because area underneath curve could represent probability. How about what is the proportion of the population that is not between 4 and 6? So we want to know everything outside of 4 and 6. So here and here. Well, for that, remember that we could use rule of complement since these are probability. So if we do 1 minus 0.16, and the reason why we do 1 minus 0.16, we know the area, the value of the area underneath this whole curve is 1. So if we subtract the area of the whole curve minus the stuff that we don't want, it'll give us everything that's not between 4 and 6. So this will be 0.84. Now here, this is asking if a value is chosen at random from this population, what is the probability that it's not between 4 and 6? So in notation, you could write the probability that x is less than 4 or greater than 6. Because this is asking you everything below 4 and over 6. So everything outside of this area. And we can compute this as the same way as we did in number 3. So this is just 1 minus 0.16, which is 0.84. Okay, so this is a probability density curve. This is also a probability density curve. But notice that this curve here is skewed to the right. And what a lot of statisticians like are probability density curve that's kind of like bell shape. And another word for bell-shaped curves are normal curves. And that's what we're going to talk about next. Okay, a continuous random variable is normally distributed or has a normally probability distribution if its relative frequency histogram is curved like a shape of a bell. So notice that this shape, this histogram, is bell shape. This is also bell shape. Bell shape, bell shape. So all of these graphs or all these histograms are normal curves. So the normal curve is determined by its mean mu and the standard deviation sigma. The figure below are different normal curves and shows how changing the mean and standard deviation affects the curve. Okay, so look at this normal curve here. It has a mean of 0 and a standard deviation of 1. If I increase my mean by 2, it pretty much just shifts my normal curve to the right 3 spaces. So it'll be 1, 2, 3. So then here the mean will be 3, but the standard deviation will stay the same. So that's what it does when you increase your mean. But here, so let's say you have a normal curve and it has a mean of 0 and a standard deviation of 1. And let's say I increase my standard deviation. And remember, standard deviation kind of like represents spread, like the measure of spread in your data. So notice that if we increase our standard deviation, the shape of the histogram or the bell-shaped curve will flatten out. It'll widen out because there's more spread in our data. So that's how increasing your mean or increasing your standard deviation, that's how it affects your graph. Some of the properties that you want to know from having a normal curve is that the normal distribution only has one mode. The mean, median, and mode are all the same. The curve is bell-shaped. Since it's bell-shaped, it's symmetric and symmetric about the mean. So that's pretty important. The normal distribution follows the empirical rule, and the area under this curve is 1. So let's look at these two different normal curves. So here below are two normal curves, curve A and curve B. So this is curve A, and this is curve B. Do these distributions have the same mean? If so, what is it? Since we already know these are normal curve, we know some of their properties is that it's symmetric about the mean. So here, curve A, it's pretty symmetric at 4, and also curve B is also symmetric at 4. So this kind of tells us that the mean of curve A is 4, and the mean of curve B is also 4. So they both have the same mean, which is mu equals 4. How about B? One of the curves corresponding to a normal distribution has a standard deviation of 3, and the other one has a standard deviation of 1. Which curve has which standard deviation? So remember, what does standard deviation measure? It kind of measures spread, right? So when standard deviation is bigger, what does that do to our curve? It kind of spreads out, right? Because again, standard deviation is measure of spread. So the biggest standard deviation, which is 3, kind of correlates with curve B because it's more spread out. So here, curve B has standard deviation of 3 since it's flatter and larger spread. And here, curve A has standard deviation of 1 since it has smaller spread. Okay, so let's not forget about the theme of this whole section. We want to figure out how to find areas underneath the curve. So before we do that, we have to remember what are z-scores. And we talked about z-scores before. So finding an area under a normal curve is a critical step in many statistician procedures. Areas under normal curves may be found by looking them up on tables or using technology. To find areas under the normal curve with tables, we must compute the z-scores. And that's what we're going to do. We could use technology, but that's required to buy really fancy calculators. And I was once a broke college student, so I know I wouldn't want to buy a very fancy calculator. So let's just use the table for now. Okay, so let x be the value from a normal distribution with mean mu and standard deviation sigma. We can convert x into a z-score by using a method known as standardization. So here, we've seen this formula before. The z-score z is just x, the value, minus mu, the mean, over the standard deviation. The reason why we want this is because z-score has very nice properties. So if the z-score was close to 0, this kind of tells us that the measure is near the mean of the distribution. If it's positive, then it's above the mean, and if it's negative, it's below the mean. So let's do a couple problems just for refresher. So let's say height in a certain population of women follow a normal distribution with a mean of 64 inches and standard deviation of 3 inches. We want to So let's say a randomly selected woman has a height of 67 inches. We want to not only find or compute the z-score, we want to interpret it too. So here, z is equal to the value x minus mu over sigma. And again, this x value is 64 minus our mean, which they gave us was, x is 67. The mean is 64 over the standard deviation, which is 3. And this is 1.0. But what does this mean? That's very important. Anyone can compute this, but we need to interpret it. So in words, we could say that a woman who is 67 inches tall is one standard deviation above the mean height of 64 inches. How about this one? Another randomly selected woman has a height now of 63 inches. We want to find and interpret the z-score of this value. So here, z is x minus mu over sigma, which is 63 minus 64 over 3, because the mean here is 64 and the standard deviation is 3. And this gives a value of negative 0.33. But to interpret this, we could say that a woman who is 63 inches tall is 0.33 standard deviation below the mean height of 64 inches. Notice that I put below. Now, why did I do that? It's because we have a negative z value. So we know that if our z-score is negative, it's below the mean. So why are z-scores so important? And how does this relate to finding area underneath curves? Well, if you remember that the only requirement for a curve to be a normal curve is that it has to be bell-shaped. Notice that all these curves are normal curves, but they all have different mean and standard deviation. Like this has a mean of 3 with a standard deviation of 1. This has a mean of 0 with a standard deviation of 2. This has a mean of 0 with a standard deviation of 1. So it's kind of difficult to find area if they all have different means and standard deviation. So what z-scores does is that it takes values from a normal curve, any normal curve, and it maps to a normal curve with a mean of 0 and standard deviation of 1, which is also called the standard normal curve. And that's what we're going to talk about next. So here, the standard normal curve. A normal distribution can have any mean and any positive standard deviation, like what I mentioned before. When values are z-scored from a normal distribution, they follow a special normal distribution called standard normal distribution. So what this means is just like what I said, it takes, if we do a z-score from a normal curve, it'll just map it into something called a standard normal curve and has a mean of 0 and standard deviation of 1. So here we have this standard normal curve. You see that it has a mean of 0 and has a standard deviation of 1. And it follows the empirical rule where 68% of the data is within 1 standard deviation away, 95% of the data is between 2 standard deviation away, and 99.7% of the data is 3 standard deviation away. Cool. And the reason why we want to do this is because standard normal curve has really, really nice properties. So here, finding probabilities and the normal curve. The area under the standard normal curve represents the probability that a randomly selected data value, z, falls into that interval. So we're going to see a lot of notation. Okay, now we're going to talk about probabilities and area underneath curves, finally. So the area under the standard normal curve represents the probability that a randomly selected data value z falls into that interval. And again, this z that we talk about, this is the z-score that we will compute. Okay, now I'm going to talk about some notation that we're going to see a lot. So when we say find the probability that's less than a value a, or find the probability of z that's less than or equal to a, this means in words that the area to the left of the value a, where a is just like a number. When we talk about the probability of z greater than a, or probability of z greater than or equal to a, this is saying the area to the right of a, where a is just, again, like a number, like a value. And when we talk about the probability of z between a and b, or the probability of z between a and b, including both a and b, this is just saying the area between a and b. So this is going to be some notation that we have to get used to. All right, so let's do a little bit of practice. So we want to convert the following into probability notation. So the area to the right of 16, we could say that this is just p of z to the right is greater than 16, or the probability of z is greater than or equal to 16. There's a little trick that I used to do, or I encourage you guys to do, is that when we see to the right of something, it kind of gives you an idea where the arrow is pointing, because I think of these as arrows. So this is pointing to the right of the value. So the arrow to the right is just this. So this is notation. How about the area between 12 and 14? Well, this is just going to be the probability of 12 is less than z is less than 14. So again, this is just notation. This is just saying what is the probability of z between 12 and 14. You could also say, or probability of less than or equal to z. Okay. How about area to the left of 1.23? So notation-wise, this is just p probability of z is less than 1.23. And again, the way I think about it is that this left tells me the direction of where the arrow is pointing. So when you look at this arrow is pointing to the left. So this is just the probability of z is less than 1.23, or to the left of 1.23. Find the area to the right of -7. So notation-wise, this is just p of probability of z that's greater than -7. And again, notice that we're dealing to the area to the right of this value. So this arrow here is pointing to the right. So that's like a trick for me to know which way, if it's greater than or less than. Now we're going to find areas to the left of data values. So what we're going to use is something called the commutative normal distribution table. Another word for it is called the standard normal table. And what it looks like, it kind of looks like this. So this is table 8.2 in your textbook. And I'm actually going to post this on Blackboard for you guys to look at it. So you could use it for homework, for quizzes, and for exams. So how do I find area to the left of data values? So let's consider this standard normal distribution. And we know this is a standard normal distribution because it has a mean of 0 and a standard deviation of 1. And this makes sense because if we take values, if we like z-scores values from a normal curve, it kind of maps into a standard normal curve. So here you want to, let's say for example, you want to find the area to the left of your z value of negative 1.58. So how do I do this using the table? Well, first you want to look at the negative 1.5 value first. You want to find that here. So here we go, negative 1.5. What I like to do, I like to highlight it. Next, I have to find the 0.08, this value right here. So this will be 0.08, and then I'll highlight it here. Where they intersect is the area to the left of that z-score, which is 0.0571. And if you look here, the area to the left of negative 1.58, if you want to do like notation, this is the probability of z is less than negative 1.58. Notice that the arrow is pointing to the left. So we're finding area to the left of this value. This is 0.0571, which is exactly what we got here, 0.0571. So let's do a couple examples. So let's say we want to find the area to the left of z equals 1.26. So what I like to do first is draw my standard normal curve. Oops. Okay, let's say this is my standard normal curve and it has a mean of 0 and a standard deviation of 1. So this is 1, and then this is 2. This is 1, 2. Oh, sorry, this is negative 1. This is negative 2. Okay, you want to find the area to the left of z equals 1.26. So 1.26 is somewhere around here. So let's say this is your z, which is 1.26. So the goal is to find the area to the left of this. So then we could use the table to figure out this value. So what we do is look at 1.2 first in our chart. So we have to go to the positive side. So this is 1.2. And then we want to look at the 0.06 value, which is right here, the third value here. So this is 0.06. And so when they intersect, which is right here, this is the area of the left of that z value. So notation, the probability of z is less than 1.26. I know it's less than because it's pointing to the left of it. And this is going to be equal to 0.8962. 0.8962. Okay, so let's do a couple example that's a little bit more challenging. So let's say a study reported that the length of pregnancy from conception to birth is approximately normally distributed with a mean of 272 days and a standard deviation of 9 days. We want to know what is the proportion of pregnancies last less than 259 days. So what we have to do is that since this is coming from a normal curve, we have to do a z-score in order to map this into a standard normal curve, which has a standard deviation. It has a mean of 0 and standard deviation of 1. So first we have to do is do our z-score. So z is equal to x minus mu over sigma. This will be 259 minus 272 over 9. Oops. And the reason why is because 259 is what our x value is, 272 is our mean, and 9 is our standard deviation. So this will be negative 1.44. Now, the goal of this is that we want to know what is the proportion of pregnancies that last less than 259 days. So notation wise, you want to find the probability of z less than negative 1.44. Next, I want to draw the standard normal curve. It kind of helps. It looks something like this, with a mean of 0 and the standard deviation of 1. Oh, there's negative 1. It's negative 2. This is also 2. Okay, so then we want to look where is negative 1.44 roughly. So it's going to be around here. So this here, since it's less than, this kind of tells you what area are we looking for. We want to find the area to the left of this. So this is going to be, we want to find the area to the left of our z-score, here z, which is equal to negative 1.44. And we could do this by going back to the table. So here, negative 1.44, we go to the negative side. We look at negative 1.4 first, which is this. And then we want to look at 0.04 here. And you want to see where did they intersect. And they intersect right here. So this just means the area to the left of your z-score of negative 1.44 is 0.0749. So this will be 0.0749. And again, I got this value from our table here. But what happens if I want to find the area to the right of a data value? So for that, we could start thinking of like rule of complements. So remember that the area underneath the whole curve is equal to 1. So if I want to find the area to the right of a z value, let's say here, if you think about it, if we take the area of the whole curve, the whole area underneath the curve, which is equal to 1, minus the area to the left of that value, all we have left is that little piece here, the area to the right of that z value. And in notation, I guess, you could write the probability of z is greater than a is equal to 1 minus the probability of z less than or equal to a, where a, of course, is just like a number. It's like it's a value. So let's consider this example here. So it's kind of the same thing with pregnancy, but we have a mean of 272 days with a standard deviation of 9 days. But here, the only difference is that we want to find the proportion of pregnancies that last longer than 280 days. And that's the key thing, is that last longer than 280. So that gives you an idea like, oh, we need to find area to the right. So first thing we have to do, of course, is like compute the z-score. And again, the reason why we compute z-score is so we could work with a standard normal curve, which has a mean of 0 and standard deviation of 1. So here z is equal to x minus mu over sigma, which is 280 minus 272 over 9. And this is going to be 0.88888 repeating. But we want to round this to do 2 decimal places because that's how we use the table. So we could round this to like 0.89. And that's important because we need 2 decimal places to use the table. So we want to find the probability of z is greater than 0.89. We know that it's greater because the keyword is lasts longer than whatever it was. And this kind of gives you the idea of like, oh, we need to find area to the right of this value. So here, let me just draw the curve. So this has a mean of 0 and standard deviation of 1. So this is -1. This is -2. This is 2. We want to find where is z, 0.89, which is somewhere around here. And we know that we need to find the area to the right of this value. So we need to find area to the right. So this whole thing. Well, if you look at the picture, this is just equal to the area under the whole curve minus the area to the right of our z value. So here again, this is our z, which is 0.89. So here we're finding the right of that z value. And again, this is just 0.89. Do we know the area underneath the whole curve? Yes, it's just 1. Do we know the area underneath the left of the z value? And yeah, we could use the table. So here, if we look at 0.89, so look at 0.8, which is here, 0.8. And then if we look at 0.09, we see that the area to the left of that z value is 0.8133. So this will be 0.8133. So then the area to the right of this z value is just 1 minus 0.8133, which is equal to 0.1867. So in words, so here, the probability of z greater than 0.89 is 0.1867. To interpret this, you could just say that the proportion of pregnancy that lasts longer than 280 days is 0.1867 or 18.67%. That's another way you could say it. Okay, so let's just stop for a moment. We know how to find area to the left of values, of z values. We know how to find areas to the right of z values. We need one last thing, is find areas between two values. So here, finding area between two data values. So this is going to be a little bit tedious, but it's not too difficult. What we could do is called the subtraction rule. So let's say you have some value z1, z2, where z1 is less than z2. To find the area between z1 and z2, find the area between these two values, what we could do is, if you think about it, if you find the area to the left of z2 and subtract the area to the left of z1, all you have left is the area between these two values. Because we already know how to find areas to the left of values, so what we could do is just subtract these two values. And this is how you could write it in notation. So let's do, again, the pregnancy example, because why not? So this has a mean of 272, standard deviation of 9. The only difference is that here, a pregnancy is considered full term if it lasts between 252 days and 298 days. And it's asking you what is the proportion of pregnancy are full term. So let's compute our z1 and z2. So now we're computing two z values. So z1, x minus mu over sigma. Here, our x will be 252. So 252 minus 272 over 9. And this is going to be negative 2.22. And our z2 here, I'm just going to call it z2. We're going to do the same thing, but with this value here, the 298 days. So this will be x minus mu over sigma, which is equal to 298 minus 272 over 9. And this is going to be 2.89. Okay, so notation wise, we're trying to compute the value z that's between the area between negative 2.22 and 2.89. So what is this going to be? So what I would do is actually draw the standard normal curve first. So here, say this is the standard normal curve that we care about. It has a mean of 0 and standard deviation, of 1. Two and 2. What we're looking for is the area between z1 and z2. Here z1 is negative 2.22. So somewhere around here, say this is z1. And z2 is 2.89. So let's say somewhere around here. Let's say this is z2. So our goal is to find the area between these two values. Okay, and again, z1 is just negative 2.22, and z2 is 2.89. Just a little reminder. So what we could do here is that this is, if we take the area to the left of z2 first, and subtract this, from the area to the left of Z1, say this was Z1, then we will have the area between these two values. So let's look at find the area to the left of Z2. And remember, Z2 is just 2.89. This is just 2.89. We could use the table. So this is the table. We have to look at 2.89 or 2.8 first, which is here. And let me erase this real quick. And then we have to look at 0.09, which is right here. So again, this value just means the area to the left of a z-score that is 2.89. So this is 0.9981. So here will be 0.9981 minus the area to the left of Z1. And remember, Z1 is negative 2.22. So here, if we could find this value, the area to the left of Z1, using the table. So I will go to the negative side here. So we look at negative 2.2, which is right here. And we want to look at 0.02, which is right here. So then we have this value here, and this is just the area to the left of a z-score that is negative 2.22, which is 0.0132. So then this will be 0.0132. So then the area between Z1 and Z2, it's going to be 0.9849. So here, the probability of the value between negative 2.2 and 2.89 is 0.9849. But how do we interpret this? Well, we could say that the proportion of pregnancies that are full term is about 98.49%. And so let's talk about like what we learned in this section. We learned basically three things: how to find area to the left of z-scores, to the right of z-scores, and in between. And these are really important to find like probabilities and proportion.